Hello, welcome to the second part of the introduction to the Easy software system. Using a high-point membrane as an example, I'd like to show you what to consider during the form-finding process and how a primary structure can be integrated into the model. This results in a combined form-finding approach in which both membrane surfaces and structural elements are taken into account. At the start of every new project, a project path must be defined. This is done by selecting a folder via the Select Folder button and then confirming the selection in the dialog window. Next, the Form Edit module is launched by clicking the first tile in order to define the necessary inputs for the form-finding process. For defining the boundary geometry, an EIN file is additionally loaded in this case. It contains the coordinates of the corner points for the high-point membrane. Via the menu path file, Open EIN File, a selection window opens. A previously prepared file can now be selected and loaded using Open. The points are now visible in the graphical interface. In our example, they are located above the zero plane in the Z direction and already define the initial position and roof edge height. Using the pencil icon in the Quick Start toolbar, the boundary is created counterclockwise as usual. By clicking near the corner points, snapping is performed automatically, ensuring that the boundary points match the predefined coordinates exactly. By clicking the starting point, the boundary is closed, and a flat mesh geometry is created, which can be visualized using the Preview function. To do this, activate the Form Finding checkbox in the Preview menu on the right-hand side. By changing the perspective while holding down the right mouse button, the flat mesh structure becomes visible. Initially, it is a regular grid. To modify it, activate the Select Boundary Properties function in the Quick Start toolbar. Then, click the central thick point located in the middle of the mesh. This opens the boundary properties in this window on the left-hand side. In the Properties panel, the mesh can now be changed to a radial mesh by enabling the corresponding checkbox under Boundary Type. The high point can be created in two ways, either via the Lift Points function in the Quick Start toolbar or by manually entering the coordinates. To simplify the selection, activate the Select Control Center Points icon in the toolbar. Then, click on the central boundary point to select it. In the Properties panel on the left-hand side, change the Z coordinate of the point from 3 to 8 meters. The boundary conditions for the high-point membrane are now defined, and the roof geometry has been successfully form-found. By changing the perspective, the result can be visually reviewed. Additionally, the resulting forces at the fixed points can be displayed and examined. To visualize these, go to the Properties panel, then under View Options in the Preview tab, check the box for Vectors Display Vectors. The force vectors are then displayed in black. Form finding is based on solving a linear system of equations using the concept of force density. The resulting equilibrium geometry is defined by the parameters in the boundary properties and the other model elements. As done previously when modifying the mesh, the Select Boundary Properties function in the Quick Start toolbar is activated, and the center point of the mesh is selected. Meshes are generally structured in two directions, the 1000 direction and the 2000 direction. In a radial mesh, the 1000 direction corresponds to the radial lines, while the 2000 direction represents the circular lines. In the Properties panel under Type Properties, the mesh settings can be configured. For the 2000 direction circular lines, the element length is specified in angles, ensuring uniform segment lengths along the circular geometry. In this direction, either the force or the resulting stress can be adjusted. In the 1000 direction, radial lines, the element length is defined in meters, and by default, the input is based on stress. The key difference is that, in the radial direction, force and stress are not linearly dependent. Therefore, their adjustment requires a more nuanced physical interpretation than in the circular direction. The equilibrium shape of a membrane structure results from the stresses and their relative ratios. If one of the stresses is modified, the shape of the membrane surface changes accordingly. To demonstrate this, we switch the view to front and observe the sag between the high point and the boundary. If we want to reduce the sag, we must increase the stress in the radial direction. This is done by raising the stress value to 1.5 kilonewtons per meter in the input field. The geometry update becomes immediately visible, as the force density method linearizes the system and requires no complex iteration. As the radial stresses are modified, the resulting forces at the boundary points naturally change as well. These forces act tangentially to the membrane surface and are directed along the element orientation at the corners. The radial elements transfer their loads to the boundary cables. To calculate these cables, the resulting tensile force must be determined. By default, this is done adjusting the so-called estimated stress. In our case, this value is set to 1.5 kilonewtons per meter. For more realistic results, this value can be set equal to the applied radial stress in radial mesh configurations. This results in a more accurate estimation of the cable forces and improves the force coordination within the form-finding process. By selecting the Select Boundary Line function in the Quick Start toolbar and then clicking the top and bottom mesh edges while holding down the Control key for multiple selection, the Boundary Cable Options window will open on the left-hand side. Modifications to the boundary cable geometry and the resulting support forces are made via the Boundary Line properties. In the Options window, under Boundary Line Settings, Arc Settings, the sag is adjusted to 8%. This directly affects the resulting support force, as the geometry and force distribution are updated accordingly. The estimated stress previously modified in the mesh settings is directly incorporated into the calculation of boundary cable forces. The corresponding results and settings can be found in the Boundary Line Properties window, under the section Boundary Line Force. There, the value can also be manually adjusted if required. The roof geometry is now preliminarily configured. The next step is to integrate the primary structure, starting with the support of the high point at the membrane center. To do this, activate the Select Control Center Points function in the Quick Start toolbar. Then, click the central point at the high point to select it. This opens the Properties panel on the left-hand side. Under Type Design, change the high point's geometry to cone. At this point, the support structure can be integrated. This is done via the Options menu on the right-hand side. Select the Strut and Bracing tab. Under Method, choose the option Cut with Z-plane, force vector used, from the drop-down list. This method only works if the form-finding preview is enabled in the Preview Options menu. In the newly visible section below, set the Z-plane height to 0. Since a primary structure requires a mixed form-finding approach, a stiffness value for both strut and cables must be provided. If these values are not yet known, the default settings can be used. However, keep in mind that this may lead to slight variations in the result during the later materialization process. The strut is now integrated into the model, extending from the 0 plane to the high point. Next, the view is switched to top view. Additional primary structures are to be placed at the corners of the membrane roof. To do this, activate the Select Corner Points function in the Quick Start toolbar. Then, in the graphical interface, click and hold the left mouse button to draw a selection box across the entire structure, which selects all corner points. The desired primary structure can now again be defined via the Strut and Bracing Options window. This time, select the option Strut and 1 or 2 cables, force vector used, from the drop-down list. In the newly displayed submenu, the Z-plane height is set to -1 by default. This means that the struts and cables end 1 meter below the Z-plane by default. To change this, we set the Z-plane height to 0, just as we did for the central support. As a result, the end positions of the elements are immediately adjusted and now lie exactly on the base level. It is important to note that stiffness values have no influence on the form-finding result. Another key parameter is the cable strut length, which defines the length of the connection element between the roof and the support. With this method, the roof edges remain fixed, and it is the position of the strut that is adjusted accordingly. The form-finding input is now complete, and the roof geometry can be visually evaluated. To improve visualization, the Polygon View checkbox is enabled in the Preview tab. This makes the mesh structure of the membrane easier to interpret. The design process is complete, and the input data can now be saved. To do this, click the Save a Form Edit File (FEF) icon in the Quick Start toolbar. In the newly opened dialog window, the current configuration can be saved using the Save button under the default settings. After that, the Form Edit window can be closed. All models displayed in Form Edit serve only as a preview within the design process. The actual form-finding procedure must now be initiated separately. In the Form Finding tab, the following steps must be carried out in the specified order by clicking the tiles with the green arrow. 1. Prepare form finding. 2. Surface elements. 3. Form finding. Only after completing these steps will the mesh, membrane surface, and primary structure of the high-point membrane be properly calculated, generated, and saved. To verify the generated and saved files, click on the Results tile. This will open the GED window, where the calculated mesh and the integrated primary structure, the so-called EIN file, are available for inspection. To achieve a more refined visual representation of the membrane, the surface polygons are also loaded. To do this, click Open Polygon File in the menu, select the file loop2d.eck, and confirm by clicking Open. To make the central support more visible, open the View options by clicking the gear icon in the Quick Start toolbar. On the left side of the window under Axes, deactivate Display Axes to hide the coordinate system and reveal the strut. By holding down the right mouse button and dragging, the object can be viewed from any perspective. All primary structures are now integrated into the model and are available for the subsequent structural analysis in the next step. We can now close the window. The design and form-finding process of the high-point membrane is now complete. In the next video of the Second Steps Easy series, we will present the structural analysis of the roof system, including various load cases and combinations, all the way to the dimensioning of the primary structure. Thank you very much for your attention. If you have any questions or suggestions regarding the procedure, please don't hesitate to post them here or contact us. We look forward to your feedback.